So let's talk about the second fundamental theorem of calculus. So we know the first fundamental of theorem of calculus gave us a way to find the definite integral on interval from a to b. A was the lower limit, b was the upper limit. Now let's say I have a situation where x is the upper limit of integration. Now keep in mind that I can't do something like this, from a to x of f of x, because these two guys can't match. So sometimes you will see if x is the upper limit of integration that we just change this to a different value, t and d of t, because we can't have that same value here and here, because that's just way too confusing. So here's what the second fundamental theorem of calculus says. If I'm taking the derivative of an integral, so think about that. I've got the derivative of an integral. So the same way I said if I gave you $5 and I took $5 from you, where would you end up? With whatever you started with, because I've given you $5 but taken it back. If I want to evaluate the derivative of the integral from 2 to x of t squared dt, and again notice these guys don't match, and I'm just going to show you the long way here. The long way says, okay, let's go ahead and do this. Let's go ahead and integrate this, and we'll leave the derivative to the end. So if I take the antiderivative of t squared, that's t to the third over 3, and I'm going from 2 to x, and so from 2 to x says take the x first and subtract when I plug in 2. And so now I'm taking the derivative of x cubed over 3 minus 2 cubed over 3. And if I wanted to, I could say, well, that's the derivative of x cubed over 3, not equals. The derivative of x cubed over 3 minus 8/3, if you'd rather. If I take the derivative of this, it's x squared. If I take the derivative of this, it's 0. And guess where I am? Back where I started. So back where I started, except here I made it a t and here was an x squared. And is that okay? Yes, because the only reason I changed this to t was because I couldn't have this x and this t be the same variable. And so that's essentially what the second fundamental theorem of calculus says. It says if it's continuous on the open interval, then if I'm going to integrate f of t from a to x and then take the derivative of that, I'm always going to end up at f of x. So I don't have to show all of the work that I just showed on the last slide, because it's always going to work out that way. I just wanted you to see that it worked out that way. So that is the second fundamental theorem of calculus. So let's take a look at a few examples, and they're not all just the super straightforward examples, because that would be too easy, right? I need to give you something to think about a little bit. So the first one is exactly what our theorem says. If I'm integrating from some value to x of t squared over t squared plus 1, I'm really just going to replace the t with the x and be done with it. The other two aren't quite as simple, because here I'm dealing with a negative x, and here I'm dealing with an x squared. So we've got a couple of different things that are going to come into play. So let's look at the number 2, the long way. The long way says let's go ahead and integrate t squared dt from negative x to x, and then we'll worry about the derivative in a little bit. So if I integrate, that would give me t cubed over 3 evaluated from negative x to x, which gives me, if I plug in x first, that gives me x cubed over 3 minus, now I'm plugging in negative x cubed over 3. Well, negative x cubed is negative x cubed, and now I'm going to keep flip change, add them together. This gives me 2x cubed over 3. Now I'm going to take the derivative of that. That's not a fraction. The derivative of 2x cubed over 3 is actually 2x squared So now what? That doesn't fit our model. Well, again, we have to be smarter than just being able to apply a formula. If I'm going from negative x to x, then essentially I'm looking at a function that looks like this. And so again, I would have from 0 to x would be x squared, and then this guy would be x squared, so 2x squared. Last one, oh so much fun, because I've got essentially the chain rule. So I'm really taking this and plugging it in, x to the 6th, but then I need to take the derivative of x squared, which is 2x. So my answer is 2x over x to the 6th, which turns into 2 over x to the 5th.